Question number 1 states that what do you call the sound wave that is heard after reflection from a hard surface? So let's see these characteristics of sound about the loudness, timbre, and the pitch. Loudness is audible strengths of sound which depend on the amplitude of the sound wave. So it is one of the characteristics of the sound wave which depends on the amplitude of the sound wave. That means the higher the amplitude, the louder the sound is. While pitch is a characteristic of sound wave which distinguishes a sharp or a high-pitched sound from the grave or dull sound. So this properties of sound depends on the frequency of the sound wave. That means the higher the frequency of the sound is, the higher the pitch of that sound is. Or the lower the frequency of the sound wave, the lower the pitches of that sound is. That means if the pitch of the sound is low, its frequency is low, and also that sound is considered as a bass. The bass is the male voices. And if the pitch of the sound is high, its frequency is also high, and that sound is called the treble. That means the female voices. So pitch allows us to hear intonations in a language and notes in a melody. Timbre is the quality of sound which allows us to distinguish between different sound sources producing sound at the same pitch and the same loudness. So timbre allows us to distinguish the vowels and the consonants that make up a word, as well as the unique sound qualities of different musical instruments. Echo is simply the reflection of the sound wave when it is reflected from the hard surface. So the correct answer is echo on D. Question number 2 states which one of the following wave is identified as longitudinal wave. So before going to answer this question, let's see what is longitudinal wave. So depending on how they propagate, we divide or we classify wave into two major groups: longitudinal wave and transverse wave. So longitudinal waves are the kind of wave which the direction of oscillations and the direction of propagations of the waves are parallel to each other. That means the direction through which the particle oscillates and the direction through which the wave propagates are parallel to each other. So examples of the longitudinal wave includes the sound wave, the pressure wave, the P wave in earthquake, and the wave on springs are some examples of longitudinal wave. While transverse waves are a kind of wave where the direction of propagation and the oscillation of particles are orthogonal to each other. Examples of transverse wave include vibrations on a string, light wave, which we call the electromagnetic wave, S wave in earthquake, wave on the surface of the deep water, radio waves, and the ripple on the surfaces of the waters are examples of transverse wave. So according to the question, just we can see that wave on the vibrating string is a kind of transverse wave. S wave of earthquake is also a transverse wave. Deep water wave is also transverse wave. Only sound wave is a longitudinal wave. So the correct answer is D. So this question says that the angular momentum of rotating object is defined as the product of it is A. Moment of inertia and angular velocity, B. Mass and 1/2 of the square of the angular velocity, C. Mass and the angular velocity, D. Moment of inertia and square of the angular velocity. So then we can see that the angular momentum of the object is simply angular momentum L is defined as the cross product is of the distance from the axis of rotation times the linear momentum of that object. Let's say that if we have an object which is rotating on a circle of radius r, this object has mass m and moving with some velocity v. This means this object has a linear momentum p. So r and p are exactly we can say it is perpendicular to each other. So we can say that the angular momentum is the product is of the distance from the axis of rotation to the linear momentum of the object is. But linear momentum of the object is defined as P is equals to mass times the velocity of the object is, the linear velocity or tangential velocity of that object is. So if we substitute this value in this, just we get that the angular momentum is equals to r mass times velocity or the tangential velocity of the object moving on the circle. So depending on this, just we know that the tangential velocity and angular velocity of the objects are related by v is equals to r times omega. If I substitute this value into the original equation, r mass times r omega, then we have m mass of the object is r square omega of the object is, or the angular velocity of that object is. So mass times the quantity, mass times the r square or the distance from the axis of rotation square is what we call the moment of inertia of the object is I. So then angular momentum of the object is the product of the moment of inertia of that object is times the angular velocity of the object is. So the correct answer is on alternative A. So question number 4 states, which one of the following statement is correct about the component of the velocity of a ball projected up at an angle of theta with the horizontal, neglecting the air resistances? So if we neglect air resistances and the projectile is projected with some initial velocity u at an angle of theta with the horizontal, so we assume that there is no any other force acting on the object or on the projectile except the gravity. So gravity is a vertical force which acting on the projectile or make it to accelerate down to the center of the earth. If we have a projectile which is launched at an angle theta with some initial velocity u, then these projectiles move through the air like this. This means the initial velocity of this projectile can be resolved into two components, the horizontal velocity component and the vertical velocity component is. So it is obvious, we know that the horizontal velocity component is the initial velocity times the cos of angle theta, while the vertical initial velocity uy is u times the sine of angle theta or the angle of projection. So in this case we can see that the horizontal velocity is always uniform motion, while the vertical velocity of the projectile is the uniformly accelerated motion, because g is acting, or acceleration due to gravity is acting vertical components of the velocity. So while the projectile is ascending or while it is moving up, the vertical velocity is decreased and it becomes 0. That means at maximum height we have the vy is 0, but vx, the velocity along the horizontal, is remain constant. So just we can say that the vertical velocity of the projectile is always changing, while the horizontal velocity of the projectile is stay constant. So vertical motion is a kind of accelerated motion, while the horizontal motion is a uniform motion. That means the initial and final horizontal velocities are always the same. So from alternative A, we see that the horizontal component of the velocity remain constant throughout its journey. So it is true. B says the horizontal velocity of the ball is equal to 0 at the maximum height is. So at the maximum height, the vertical velocity is 0, not the horizontal velocity. The horizontal velocity remain constant throughout all the journey. C says the vertical component of velocity remain constant throughout its journey. So this is completely wrong, because the constant velocity is not vertical, it is the horizontal component of the velocity. D says that the vertical component of velocity increases while the horizontal component velocity decreases. So the horizontal velocity do not change, it's always constant, since the horizontal motion of projectile is always a uniform motion, and the vertical component of velocity is not always increase, it can be decreased while the object is ascending up, and again increases when the object is descending down. So D is completely false, C is also false, and B is also false, and the correct answer is on alternative A. So this question states that which one of the following statement is correct about the electric field due to a charged spherical solid conductor? A. It is non-zero constant inside the sphere. B. It is parallel to the surface of the sphere. C. It is zero inside the sphere. D. It is non-zero constant outside the sphere. So let's consider a conductor, solid conductor like the spherical shape is. If this is our conductor, and from the Gauss law, we know that if a conductor is charged, charges are always distribute themselves on the surfaces of that conductor. So let's say this spherical solid is charged with a positive charge. Those charges always distribute themselves on the surface of the conductor because charges are free to move through the conductor. So due to the repulsions of these positive charges, they repel each other and resides themselves on the surfaces of this conductor. So the electric field of these charges are always perpendicular to the surfaces of this sphere, not the parallel. So in all direction we have the field which is radially outward from these charges if we have a positive charge, but if it is negatively charged, these electric fields are inward or into the charges. And also inside the sphere we have the charge which is out of these positive charges. So these are the field inside the spherical conductors. So by symmetry we can see that the field inside the conductors are opposite to each other and they cancel, and finally we have zero electric field inside conductor and the remaining electric fields are always outside that conductor, and it is also perpendicular to the surfaces of that conductor. So the correct answer is on alternative C, which says it is zero inside the sphere. That means the electric field or the static electric field of any conductor is always zero inside that conductor. So a metal wire made of a coefficient of linear expansion alpha is heated so that its temperature is changed by delta T. If the length of the wire before heating is L0, which one of the following expression is correct for the final length of the wire after heating? So this is the linear expansions. So if we have a wire of length L initially at the temperature T0 and we heated this conductor by some temperature and its temperature is changed, and then this wire expands or it's linearly expand and some delta L length is added to the original length of the wire. So at temperature some T final. So the temperature is changed by delta T, which is T final minus the T node. So the linear expansions of the solid depends on three things. That means it is depends on the temperature change, the original length, and the type of the material we are heating, or the coefficient of the linear expansions of that material. Then we can easily that delta L means, that means the linear expansion means simply the final length L minus the initial length of the material which is heated, or the solid which is heated. So when we substitute, and easily we can see that L minus L naught is equals to L naught times alpha delta T, and then the final length of the solid become L naught 1 minus alpha delta T. So this is the final length of the wire which is heated. So we can see that the correct answer is on alternative A. The final length become L naught into 1 minus alpha delta T. Question number 7. What amount of heat energy is required to completely melt 200 grams of an ice at 0 degrees centigrade? Take the specific latent heat of melting for ice is 3.3 times 10 raised to 5 joule per kilogram. So this means the amount of energy required to melt the ice of 200 grams at 0 degrees centigrade into water completely. So that means we have a latent heat of fusion. So the amount of heat energy needed, which converts the amount of the solid into the equal amount of liquid, is the heat of fusion we have. So the heat of fusion is mass of the object is times the specific latent heat of fusion, that substances. So since we have the water, the mass of the water is equal to 200 gram times the latent heat of fusion of water is 3.3 times 10 raised to 5 joule per kilogram. So if we convert 200 gram into kilograms, we have 0.2 kilogram times 3.3 times 10 raised to 5 joule per kilogram. So this kilogram cancel with the kilogram, and 0.2 times 3.3 is simply we have 0.66 times 10 raised to 5 joule. So the amount of heat energy needed become 6.6 times 10 raised to 4 joule. So the correct answer is on alternative D. So this question states, question number 8, the orbital speed of satellite at height of 780 km from the surface of the Earth is 7,465 meters per second. Then what is the period of this satellite? So we know that when the satellite is moving, consider this is the Earth, here is as a radius RE, which is 6.4 times 10 raised to 6 meter, and the satellite is situated at a point 780 km above the surfaces of the Earth. So this satellite is moving with the velocity of 7,465 meters per second. Then what is the period of revolution of this satellite, or how long will this satellite take to revolve one round around the Earth? So to find this, just we know that we can find in either ways, that is the speed of the satellites, or these satellites cover the circumferences of this orbit. So the distance it can cover in one revolution is 2 pi times r, where r is now the distance measured from the center of the Earth up to the satellite. That means r is equals to the radius of the Earth plus the height above the surfaces of the Earth for that satellite. So the time it takes to complete one full revolution or one full circle is what we call the period, and the satellite is moving with the velocity v. So this velocity v is equals to, so s over t, the distance is 2 pi times r divided by period of satellite t. So then from this equation, the period of satellite can be calculated. T is equals to 2 pi r divided by the orbital speed of the satellite. So this, the period or the orbital period of satellite is 2 pi times r is radius of the Earth plus height h above the surface of the Earth divided by the orbital speed of the satellite. So if we substitute all the values, 2 times pi is 3.14, radius of the Earth is 6.4 times 10 raised to 6 meter plus h is 780 kilometer. So we can convert into meter, and divided by the speed of satellite, orbital speed of satellite is 7,465 meter per second. So if we manipulate this value, the period, orbital period of the satellites become 6.04 times 10 raised to 3 seconds. So the correct answer is on alternative D. So this question states, the charges of a 20 microcoulomb is stored on the capacitor when a potential difference between its two parallel plates is 200 volt. What is the capacitance of this capacitor? So we can easily do that. The charge on the capacitor is 20 microcoulomb, and the potential difference across the terminal of the capacitor is 200 volt. Then what will be the capacitances of this capacitor? So we know that from the definition of capacitance, capacitance is equals to the charge stored on a capacitor divided by the potential differences of the capacitor between the terminal of the capacitor. This is equals to 20 microcoulomb divided by 200 volts. So this 0 can be cancelled with this, and this 2 by 1, that means we get exactly 0.1 microfarad. That means coulomb per volt is farad, so the capacitance of the capacitor is 0.1 microfarad. So the correct answer is on alternative A. Question number 10. An air-filled parallel plate capacitor is connected to a potential difference V to store electric charge. If the area of the plate is A and the separation between the plate is D, then the electrical energy stored on the capacitor is... So the energy stored in a capacitor is given by, simply if we have a parallel plate capacitor, the capacitances of the parallel plate capacitor is given by the dielectric constant between the plates of the capacitor, permittivity of free space epsilon naught, area of the plate divided by D. So now A is area of the plate, D is the separation, K is the permittivity of the material or the dielectric constant. In this case, the capacitor is air-filled, that means K become 1. So the capacitance of the air-filled capacitor is epsilon naught A over D. So the energy stored in this capacitor can be expressed by the electric energy stored in a capacitor is a half of C times the potential difference square V. So C is the capacitance, V is the potential difference between the terminals of the plates of the capacitor. So if I substitute the values of C here, this is a half of C is epsilon naught A over D times the V square. So this is easily can be manipulated as epsilon naught A V square over twice of D. So this is the energy stored in the capacitor. So the correct answer is on alternative B. The gauge pressure at a point in a fluid at rest is defined as... So when we see at the absolute pressures of the fluid at rest, so consider any fluid which is at rest, and we want to find the absolute pressures of this fluid is at point P. So this absolute pressure is always given by absolute pressure at point in a fluid is the sum of the atmospheric pressures and the pressure due to the coulombs of this fluid. So the total pressure at this point is simply the P atmospheric pressure plus the pressures of the fluid due to the height is H, or pressure due to the column of this fluid, which we call the rho G times H. So this is the total pressure at this point is, and the atmospheric pressure is pressure due to the air column above the surface of the fluid, and rho GH is the pressure due to the fluid columns, which we call the gauge pressure of the fluid. So gauge pressure rho GH is defined as the absolute pressures at the point is minus the atmospheric pressure. So gauge pressure is the differences of the absolute pressure and the atmospheric pressure. So the correct answer is on alternative D.